In this lesson, we'll learn to write the equation of polar curves from their graphs. There will be three types of graphs that we'll concentrate on, and three sort of approaches. There are the simple graphs, number one. Those are going to be your circle that's centered at the pole. That's going to have an equation in the form r equals a number. And then a line that passes through the pole, and that's going to be in the form theta equals a number. So those are our two simplest equations to write. We can write them directly from the graph. Number two, for a more complex polar graph, that is a limacon, a rose curve, or a spiral, we're going to use the graph to plot the relationship with r and theta on the vertical axis. And so r is on the vertical axis and theta is on the horizontal axis. And then we're going to use that graph to write the equation. And then thirdly, for other graphs that really don't look like a polar graph, so a line that doesn't pass through the origin, a circle that's not centered at the origin, we're going to write those equations in rectangular form first and then convert to polar form. So in example one, we see a spiral. That is clearly a polar graph. So I'm going to use this technique of making a graph and transferring our points onto that graph with r on the vertical and theta on the horizontal axis. So let's label some points on the graph first. This point right here is going to be my starting point. That has an r value of 1 with a theta of 0 degrees. Now I'll go to my next quadrantal value. That has an r of 2 with a theta of 90 degrees. Next quadrantal value, radius is 3 with a theta, or an angle, of 180 degrees. And then the last point, the radius is 4 with an angle measure of 270 degrees. Something I want to emphasize about this graph is there is a hard start and stop on this graph. This graph is not continuous. It doesn't loop back on itself. So this graph will have to have a restricted domain. So let's plot first, and then we'll talk about that restricted domain. So for our theta values, we're going to need 0, 90, 180 through 270. And then for our r values, 1, 2, 3, and 4. So we have at 0 degrees, we have a radius of 1. At 90 degrees, we have a radius of 2. At 180 degrees, we have a radius of 3. And at 270, we have a radius of 4. If you connect those points, that's very clearly a straight line. We know how to write the equation of a line in the form y equals mx plus b. But in this case, y is not really y. Y is the vertical variable. And our graph has r as the vertical variable. So this will be r equals. And now let's find our slope, our m value. Our m value will be positive since the line is rising from left to right. And our rise is 1 for every run of 90 degrees. So that means that the slope of this line is 1 over 90 degrees. Now, if you don't put that degree marking there, that's fine. And we'll replace our x, our horizontal variable, with theta, since theta is graphed on the horizontal axis. And then plus b, which would be the y-intercept, or in this case, the r-intercept, is 1. One last thing that we need to do with this equation is we need to put a restriction on the values of theta. The only theta values that are graphed range from 0 through 270. So you can write a three-part inequality that says that this is the equation of the graph only for theta values in between 0 and 270. Make sure that your inequality has those inequality symbols pointing toward the smallest and toward the 0 degrees. All right, now let's look at B. This is also clearly a polar graph. We're going to use the same technique on it. So we'll create a graph with r on the vertical and theta on the horizontal. Let's name some points on this graph. There are two places that you can start on this graph. You can start on the 0 degree axis, and there are really 2 points that are showing up there. I would encourage you to start with the larger of those two. I think that will be much easier, and it'll give you R values that are for the most part positive. So that first point has an R value of 6 for a theta of 0 degrees. Then if we go to our next quadrantal value, the R value shrinks to 2 for a theta of 90 degrees. So we can see that that graph is sort of spiraling inward there. Then what interesting happens in the next quadrant is the R goes to 0. Every time the graph passes through the pole, R is 0, and then as we continue, R becomes negative. So when we get to our next point on the graph, this is actually a negative radius, -2, at a theta value of 180 degrees. And then continuing back around, theta becomes positive again. And then we have an R of 2 and a theta of 270 degrees. And then continuing to the end of the cycle, we end with an R value of 6 and theta equals 360 degrees. Now we can plot all of these on this vertical and horizontal axes. And we're going to need R values that go from a lowest value of -2 to a middle value of 2 and a high value of 6. And we'll need all of our quadrantal values on the graph. So we start out with an R value that is 6 when theta is 0 degrees. R shrinks to 2 at theta equals 90. And then when we get to 180, the R, it becomes -2. At 270, R is 2 again, and at 360, R is 6 again. If we connect this graph, sorry for my lousy sketch there, you can clearly see that this is a cosine, and it's a right side up cosine. It's been shifted up 2, so I'm going to start with 2 plus, and the amplitude of this cosine is 4. So R is equal to 2 plus 4 times the cosine of theta. You can put the plus 2 after the cosine of theta if you wish as well. Either order is fine. All right, let's shift to a different approach this time. This graph clearly does not look like a polar graph, right? It looks like a plain old y equals mx plus b type of graph, a straight line. So on these, I would encourage you to kind of sketch in your x and your y axis, because we're going to write the equation in y and x first. So for this line, we know it's in the form y equals mx plus b, and our slope can be found using those two intercepts. I would encourage you to use sort of the y-intercept and the x-intercept to find the slope. Goes up 2 and over 4, so it looks like our slope is 2 over 4 or 1/2. So y equals 1/2 x, and then our y-intercept is -2, so -2. It will be easier to convert an equation if it's in standard form, that is to say, no fractions. So let's multiply everything by 2. 2y equals x minus 4. And then I'm going to swap the 4 and the 2y, add 4 to both sides, subtract 2y from both sides. From this point, we can replace x with r times the cosine of theta, and y with r times the sine of theta. In order to solve this for r, you can factor out the r, and then divide. So r is equal to 4 divided by the cosine of theta minus 2 times the sine of theta. That is one possible answer. I do want to emphasize there's another answer that you might get if you move things to the different side of the equation. This one's equivalent. For this answer, the numerator and denominator will be exact opposites of the numerator and denominator in the other answer. If we change the sign of both the numerator and the denominator in a fraction, the fraction has the same value. So if your answer is in one form and you have opposites of the numerator and denominator, your answer is equivalent, and therefore just as good. All right, let's check out D. D is very clearly a polar graph. So let's actually use that strategy where we're going to plot where R is vertical and theta is horizontal. Okay, for this graph, we have to have a very clear picture of where we're starting. So I want to draw your attention to this little wedge right here. That's the wedge that represents theta moving from 0 to 30 degrees. You notice that there is no graph contained inside that wedge. Since there's no graph contained inside that wedge, the R values for 0 to 30 degrees must be negative, and that graph is actually appearing in the opposite quadrant. So our action is going to take place in quadrant 3 to start with, but our angles will be quadrant 1 angles, and R will be negative. So what do we see happening first? From 0 to 30 degrees, it looks like our R value is going from 0 down to -4. And then what happens next is, as we trace out the rest of the graph, R goes back to 0 again. Now, I don't know exactly where this occurs, but I'm going to guess if it took 30 degrees to get from 0 down to -4, it's going to take another 30 degrees to get back up to 0. And then let's continue tracing the graph. From there, the graph heads back into quadrant 1. That means that R became positive again. So between 60 and 90, the R values increased to +4. And then, again, I'm just going to hazard a guess here that it's going to be 120 or 30 degrees later where R returns back to 0. Now we can connect the dots because we've got a full cycle. This clearly looks like a sine curve. It also looks like an inverted sine curve. So when we multiply for the amplitude, we'll make that multiplier a negative. There's no vertical shift on this one. So R is just equal to -4 times the sine of, and what we'll notice here is that one cycle of this sine curve did not take 360 degrees as the parent function does, but took only 120 degrees. That means our multiplier for theta must be 3 because the period was shrunk by a factor of 3. So our equation there is R equal to -4 sine of 3 theta. All right, let's check out the next one. Sometimes it can be confusing to look at polar graphs and decide whether it's a circle or a limacon. Look really carefully at the graph. This one really does look like a circle. If it looks flattened at all, it's really a limacon. All right, so for this one, a circle is probably easiest for us to write in y and x form or rectangular form. So I'm going to superimpose a y and an x-axis on top of this graph. And we'll have a center of the circle. And the center is generally known as h, k. And our h, k value is 0, -3. That's where our center of the circle is. And the radius of this circle is 3. The general form for the equation of a circle is x minus h squared plus y minus k squared equals r squared. H being the x-coordinate of the center, and since our x-coordinate is 0, x minus 0 is just x, so that's going to translate into x squared. Since k is a negative value, y minus k will be y plus 3. So y plus 3 squared equals, and if the radius is 3, r squared is 9. So there's our equation in rectangular form. To convert into polar form, go ahead and expand or multiply out y plus 3 squared. That's y plus 3 times y plus 3, which gives us y squared plus 6y plus 9. And I'll bring down the 9 on the other side. A quick algebraic thing that we can do to both sides is subtract off that 9. And then let's go ahead and let's subtract 6y from both sides. What that'll do is it'll separate out our x squared plus y squared, which can be replaced with r squared, and y can be replaced with r times the sine of theta. In order to solve this one for r, there's an easy way to do that, and that is just to divide both sides by r. So if we divide both sides by r equals -6 times the sine of theta is the equation of that graph in polar form. Okay, I do have a few for you to try. Pause the video and try this one on your own. Hopefully you realize that this is one of the simpler polar graphs. And if you didn't recognize it, what I want you to think about here is I want you to think about naming several points that are on this graph. So I just looked at the point that's 2, 60 degrees. Here's another point, 3, 60 degrees. Here's another one, 4, 60 degrees. So when we're writing the equation of this line, we want to think about what all these points have in common. Well, they all have the same theta value. Even the ones on the other side could be, for instance, -1, 60 degrees. Now, you could say theta equals 60 degrees, and that'll be correct. You can also say theta equals 240 degrees using the quadrant 3 portion of the graph, and that'll also be correct. So there are multiple correct answers here. All right, let's try B. Try this one on your own and pause the video. Okay, you should have gotten r equals 2 times the secant of theta for this one. We have to recognize that this is not really a polar graph, so we can just sort of superimpose that x and y axis. And then if you're thinking about rectangular coordinates, what you can notice is that all the points on this graph have the same x value, and that x value is 2. So x equals 2, replace x with r cosine theta, and then solve for r. Okay, one more for you to try. Let's try C. Pause the video while you do this. The equation of this rose curve is r equal to 5 times the cosine of 2 theta. If you follow the trace around, you'll see that orange set of arrows that I drew. That's r going from +5 at 0 degrees to -5 at 90 degrees. And then if you follow the blue arrows, that's r going from -5 at 90 degrees to +5 at 180 degrees. So that'll give you a full cycle. And since the full cycle takes place in 180 degrees, the multiplier of theta must be 2 because we've shrunk the period by a factor of 2 from 360 to 180. And hopefully that gives you a pretty good idea of what you can do on a rose curve. Just one other thing to mention, you can also figure out some things about rose curves by their number of petals. This had 4 petals on the rose curve, and if you have an even number of petals, you can divide that number of petals by 2 just to find the coefficient of theta. So that's another kind of thing to add to your bag of tricks when converting graphs into their polar equations. All right, that's it for the video.